We've just looked at some laws and some standards. Laws and standards are different. Laws are created by legislative bodies which are part of the government. An example of a legislative body is the United States Congress. Standards, meanwhile, are developed by government agencies. The standards help individuals and corporations to implement laws. An example of a government agency is NIST. FedRAMP and FIPS 142, they're two examples of standards developed by this government agency NIST. The US Congress cannot create a law on its own. The US President must sign the bill. Congress, con means with or together. This is one way of remembering that Congress is the overarching term for the House of Representatives and the Senate. This is somewhat similar to the House of Commons and the House of Lords in the United Kingdom. Senators are more likely to be senile. The term for senators is 3 times as long as the mere 2-year term possible for members of the House of Representatives. So House of Representatives, if they're elected, stay there for 2 years. What is a law? There are scholarly disagreements over the concept of a law. For example, there's a question over whether it is possible for the US government to create a law which you ought not to comply with. However, pretty much everyone agrees that legal systems consist of rules. Laws are rules. And a significant number of intelligent AWS resources or constructs within the AWS product are rule-governed, and we've seen that already with the load balancers. But this includes route tables, elastic load balancers, auto-scaling, and firewalls. It's therefore important that our conception of a rule isn't overly restrictive. So it's important we know what we mean by a rule. If we didn't, it would prevent us from properly understanding those AWS constructs. Rules are if-then statements. For example, if you park on the yellow lines, then you will receive a £100 penalty notice. And similarly, here is a rule you might find in an ACL, a network access control list. If the traffic is on port 80, then it will be rejected. Historically, some asserted that all legal rules threaten us in some way. That's what it is to be a legal rule. We do not park on yellow lines because we're threatened by the fine. It's implicit, of course, but ultimately we are coerced in the same way that a bank teller would be persuaded to put cash into a bag by a sawn-off shotgun. We don't steal from the supermarket Tesco because we're threatened by prison. Essentially, all legal rules are an order backed by a threat. However, we can see that this view of legal rules is too narrow, and you should certainly not limit your conception of rules in this way. Consider the variety of rules for a moment. There are laws for getting married and civil partnerships. There are laws for making wills. What is the threat here? So something else isn't going on. It doesn't work to think of all legal rules as threats. The law regarding marriage sets out certain conditions, and it implicitly says, if you fulfill these conditions, then your marriage will be valid. Examples of fulfilling the conditions? Well, it's just things like employing an official registrar and notifying the local authority. You meet the conditions, a valid marriage is created. These sorts of rules are fundamentally different from the rule telling us not to steal from Tesco or park on yellow lines. The philosopher John Searle has a term for them. They are constitutive rules. And H.L.A. Hart, another philosopher, called them power-conferring rules. This is because such rules don't merely regulate a pre-existing activity. Rather, there would be no activity without the rules. The rules constitute the activity. So John Searle called them constitutive rules. Searle gives the example of rules in cricket. They're the stuff of cricket. There was no chaotic cricket which existed pre-regulation. Rather, somebody decided to lay out the conditions that had to be met to score a run, and that was the game. This is similar to the way the law around marriage sets out conditions to be met. The rule around marriage gives us means to achieve certain desires, if we were to have them. The rule concerning stealing is different. It gives us reason to reconsider our desire to steal. The rule concerning marriage confers a power on us. We have the power to get married. So I'm showing there that there's a different way of thinking of rules, and we can even think of that rule against stealing as shaping our desires. You could think of it as giving us reason to reconsider the desire to steal. It's important that you have this wider conception of rules. It's necessary for understanding route tables. There are two columns on a route table: destination and target. We can think of the target column as conferring upon packets the power to reach their destination. If you want to arrive at a destination on the internet, then go to the internet gateway. More generally, if you want to form a valid marriage, then do such and such. Same kind of idea. Now consider the desired capacity parameter, which you must specify in EC2 autoscaling. Informally, we can think of there being an autoscaling agent. There's not an agent in the technical sense, meaning a program that runs in the background, or anything similar to a CloudWatch agent, but this is just an informal thing. Now, to understand how this auto-scaling agent operates, consider an analogy with a citizen. First, a citizen has underlying things it cares about that they care about. Their personal projects, and arranging a marriage, arranging a will, etc. Second, a citizen has a means to make these things official. That is, rules to create a valid marriage or will, etc. Third, the citizen might desire things, and the law says no. For example, they might desire to steal from Tesco a packet of crisps. So, three things: underlying values, like personal projects, means of protecting them should we desire, and limits on our desires. And each of these three elements is found in an autoscaling agent. First, it cares about some underlying feature. This might be the CPU utilization of the instances or the total number of bytes sent in or out. It cares. Second, it gives some means, it is given some means to achieve how much CPU each instance must deal with. But in this situation, its means are twofold: adding instances and removing them. Third, there are limits on the number of instances it can desire to have. And that's like the way the law limits your desire if you do desire to steal crisps, for example. And it's the same thing here. There are limits on the desires that this autoscaling agent can have. And these are the max capacity and minimum capacity parameter in autoscaling. We've just considered rules while considering NIST, the National Institute of Standards and Technology. We were exploring NIST because it has a campus in Boulder, and we talked about how buildings in Boulder are regulated by policy, for example the Danish Plan. Boulder is also famous for Pearl Street Mall and a university. The university in question is usually referred to as CU Boulder. The CU stands for Colorado University. At CU Boulder, there were two researchers, Darren Hardy and Michael Schwartz, and they were involved in something called the Harvest Project. The authors wrote, "We call the system Harvest to connote, meaning suggest, its focus on reaping the growing crop of internet information. While Harvest's initial focus is on resource discovery, the architecture encompasses the more general issue of making effective use of information." Darren Hardy and Michael Schwartz. This system, which was funded by the Advanced Research Projects Agency, ARPA, was dealing with this problem. It was hard to find relevant information on the internet. They tell us that the harvest system can be configured to automatically collect and summarize related objects from around the internet into a large collection, or to collect, summarize, and hand annotate a tiny specialized collection. Harvest automates many of the tasks needed to integrate information from disparate repositories and formats. Harvest's architecture makes efficient use of internet servers and network links, and our measurements indicate that Harvest can reduce server load, network traffic, and index space requirements by 1 to 2 orders of magnitude compared with previous systems. In one expression, their concern was with web caches. But the project came to an end in the year 1996. The project was continued at the University of Edinburgh in the UK. Crucially, the object cache developed by the Harvest system was carried forward into a new open source project entitled Squid. Notice how the Harvest project came to an end in 1996 and version 1.0.0 of Squid is released in July, the summer of 1996. Dwayne Wessels was important in this. He spoke on Squid in 1997. In 2004, he wrote a textbook published by O'Reilly entitled Squid, the Definitive Guide. And its blurb says, by caching and reusing popular web content, Squid allows you to get by with smaller network connections. It also protects the host on your internal network by acting as a firewall and proxying your internal web traffic. You can use Squid to collect statistics about the traffic on your network, prevent users from visiting inappropriate websites at work or school, ensure that only authorized users can serve the internet, and enhance your privacy by filtering sensitive information from web requests. Clearly, a system such as Squid, which is used for proxying your internal web traffic, might be interested in maintaining the ability to discover the source IP address of a packet. Because a proxy is something which represents another thing and acts on its behalf. And so when a client or a machine uses a proxy, has something act on its behalf, well, whatever's on the other end might be interested in who's the person behind the proxy, who's the source IP address. So that's that connection. Squid seems to have introduced the X forwarded for header. And this is simply stated without evidence by Matir 2020. Source in the description. So that's the origin story of the X forwarded for header. It's been around at least since 2010, and perhaps the feature was in Squid since its inception in 1996. X forwarded for. It's the oldest of the free solutions and was probably introduced by the Squid caching proxy server. As the X- prefix implies, it's not an official standard. It's not in an RFC from the Internet Engineering Task Force, or IETF. So it's a bit informal. The header is an HTTP multi-valued header. So many values in the header, which means that it can have one or more values, each separated by a comma. Each proxy server should append the IP address of the host from which it received the request. The resulting header looks something like this. So this is what it looks like. We'll have uppercase X, X forwarded for with dashes, then a colon, and then client, comma, proxy 1, comma, proxy 2. So just step back, sense check. X forwarded for, meaning X forwarded on behalf of. and the colon means we're going to say, okay, who did we do it on behalf of? But what if you have an original client at the beginning of the chain? They send a message and it goes to a proxy, but then the proxy passes it to a second proxy and it passes to a third proxy. What if that happens? Well, the idea is the relative originator gets put here. We keep adding the IP, some identifier for the client here. Okay, so I'm using the term relative originator. If we have a client who passes a message to a proxy, who passes it to a second proxy, then the first proxy is a relative originator compared to the second proxy. Let me put it another way. From the second proxy's perspective, the first proxy is the originator. Of course, it isn't the absolute originator because that's the client right at the beginning of the chain, but it is the relative originator. And so we say each proxy server, in case there are many, each proxy server should append, meaning add on, each proxy server should append the IP address of the host from which it received the request. In other words, the IP address of the host, which was, for it, the relative originator. This would be a request that has passed through 3 proxy servers. The IP of the third proxy would be the IP seen by the application server itself. Often referred to as the remote address or remote ADDR in many application programming contexts. So here, even though we've got client proxy 1, proxy 2, we're saying that there are 3 proxy servers involved. We know there are 3 because it's the ultimate receiver of the packet that looks at so let me make the point another way. We only print something here once when we need to print the previous IP address. So by the time we've put client here, there's already 1 proxy. By the time we're printing proxy 1, well, it's proxy 2 is looking back, so we already have 2 proxies involved. And by the time we're printing proxy 2, we've already got 3 proxies involved. And that's a bit of why it's like that. That's a bit of why, even though we have proxy 2 written here, there are 3 servers involved. Because this is from the perspective, what we print is the IP address, which is, from the perspective of the current thing, the previous IP address. Now, in practice, let's fill out those general markers, because client and proxy 1 and proxy 2 written here are just general placeholders. In reality, you might see something like this, which is an IP version 6 address, 2001:db8::6. Here's another IP address, 192.0.2.1. Coming from a TCP connection from 127.0.0.1. This implies that the client had IPv6 address 2001:db8::6 when connecting to the first proxy. Then that proxy used IPv4 to connect from 192.0.2.1 to the final proxy, which was running on localhost. A proxy running on localhost might be Nginx, splitting between static and application traffic, or a proxy performing TLS termination. So that's a bit about X forwarded for. What about proxy protocol then? This is something different. This was essentially developed by a Frenchman called Willy Tarot. Proxy protocol has its own specification document, and the first version of the document is 29th of October 2010. It was a Friday. We can be absolutely certain that the X forwarded for header is older, because the proxy protocol is responding to its weaknesses. Tarot in 2010 this is when he's writing, begins by explaining the basic problem. Relaying TCP connections through proxies generally involves a loss of the original TCP connection parameters, such as the source and destination addresses, ports, and so on. And that's problematic. Taro goes through a list of historical solutions. There are 3 historical solutions. 1, the X-client protocol, all uppercase, the X-client protocol. This is particularly suited to mail exchanges. 2, the forwarded extension. This is for HTTP. Taro explains that it's aimed to replace the omnipresent X forwarded for extension. That it aimed to replace the X forwarded for extension, the forwarded extension. Now, the forwarded extension is set out in a 2014 RFC written by Andreas Peterson and Martin Nilsson. And third solution is dumb proxies. They're dumb because they process protocol agnostic data. An agnostic, if we're talking about religion, is someone who says, I don't know whether God exists or not. I'm not saying God does exist. I'm not saying I'm an atheist and God doesn't exist. So if here we talk about a protocol agnostic data, you're saying you're on the fence when it comes to protocol. You're compatible with any protocol. So a dumb proxy, it's dumb because they're agnostic about the protocol. Examples given are STUML and STUD. Taro writes, they talk raw TCP on one side and raw secure sockets layer on the other one, and they do that reliably, without any knowledge of what protocol is transported on top of the connection. Taro's own HA proxy is an example of a dumb proxy. The problem with the X-client protocol, that should be written all uppercase, and the forwarded extension, is that they require a knowledge of the underlying protocol to be implemented in the intermediaries. What's wrong with using dumb proxies? Well, Taro suggests the problem lies with combining proxies. He writes, the problem with such a proxy when it is combined with another one, such as HA proxy, is to adapt the dumb proxy to talk the higher level proxy. Admittedly, the author's limited knowledge prevents me from fully appreciating this problem. Perhaps it's the fact that only one X forwarded for header can be put in place, and once it's there, it's there. That's part of the problem, maybe. For instance, Taro writes, a patch is available for STUML. STUNL? How do you spell that? STUNL or STUML? I've spelt it STUML, M for Mike here. 2 M's, where M is for Mike. A patch is available for STUML to make it capable of inserting an X forwarded for header in the first HTTP request of each incoming connection. HA proxy is not able to add another one when the connection comes from STUML, so that it's possible to hide it from the servers. Notice how HA proxy is not able to add another X forwarded for header, and that's the problem. The following paragraph from Matir 2020 explains things quite well. The author has just explained the X forwarded for header, which was introduced by Squid, remember? The author has then gone over the forwarded header, introduced in 2014 in RFC 7239, and he points out that both of those headers, X forwarded for and forwarded, both of them are HTTP headers, and one consequence of this is that a pure TCP load balancer, which cannot see content at layer 7, because TCP is at layer 4, it will miss out on all the fun. And it's here that proxy protocol enters, Willie Taro's invention. We're told, at this point, you may have noticed that both of these headers are HTTP headers, and so can only be modified by a layer 7 HTTP or layer 7 proxy or layer 7 load balancer. If you're using a pure transmission control protocol load balancer, TCP load balancer at layer 4, you'll lose the information about the source of the traffic coming into you. This is particularly a problem when forwarding HTTPS connections, where you don't want to offload your TLS termination. But you still want information about the client. So it's particularly a problem when forwarding connections where you don't want to offload your TLS termination. Perhaps traffic is going via an untrusted third party. So you don't want to offload your TLS termination, but you do still want information about the client. So you want something to be maintained, but at the same time, you want to keep in control of the TLS termination. Clearly then, it's usually the case that if you need information about the client, then you simply must offload the TLS termination. That's the background here, isn't it? That usually that holds. If you want information about the client, you've got to offload the TLS termination. The price of gaining that information about the client is offloading the TLS termination. The author is making the point that sometimes, in fact, you want to have your cake and eat it. You want that information about the client, but you don't want to offload your TLS termination. Well, Proxy Protocol can help with this. To that end, the developers of HA Proxy developed the Proxy Protocol. There are currently 2 versions of this protocol, but I'll focus on the simpler and more widely deployed first version. The proxy should add a line at the very beginning of the TCP connection in this format. So let's take a look. So it's just a line, begins with proxy, all uppercase letters, and then we'll have the protocol, the source IP, SRC IP, the destination IP. So remember that it's first the source, then the destination, which makes sense from left to right. Then the source port, the destination port, and then they've put \r\n. Note that unlike the HTTP headers, this makes the proxy protocol not backwards compatible. Sending this header to a server that's not expecting it will cause things to break. Consequently, this header will be used exclusively by reverse proxies. And a reverse proxy is a proxy which, rather than representing the client, represents the server. So, proxy protocol is a header, but it's not an HTTP header in the way the X forwarded for and the forwarded headers, they are HTTP headers. This is a building in France. This is one of the headquarters used by the company HA Proxy Technologies. This is in Antony, about 7 miles south of the centre of Paris. How does this all relate to load balancers on AWS? Well, first let's consider the classic load balancer. I presume that the X forwarded for header, with its origins going back to UC Boulder, was present the moment elastic load balancing burst onto the scene in 2009. We know that just 1 year later, in 2010, this was expanded to include the X forwarded proto for protocol and X forwarded port headers. So this is from an AWS documentation. You can see that in 2010, support for X forwarded proto and X forwarded port headers was added. The X forwarded proto header indicates the protocol of the originating request, and the X forwarded port header indicates the port of the originating request. The addition of these headers to requests enables customers to determine if an incoming request to their load balancer is encrypted, and the specific port on the load balancer that the request was received on. That's because some protocols like HTTPS indicate encryption. For more information, see HTTP headers and classic load balancers. So that's 2010. Then, 4 years after the classic load balancer had been on the scene, the new innovation, pioneered by Willie Tarrow, was added: PP, Proxy Protocol. So support for Proxy Protocol. These are extracts from the end of the AWS user guides where they say when they made changes to their documentation. So in 30th of July 2013, added information, read, about Proxy Protocol support for load balancers configured for TCP and SSL connections. The X forwarded for header is automatically added on the CLB. Automatically. Meanwhile, the Proxy Protocol was part of what I like to call the 8 funky things which could be configured. So one was automatic and one was configured. Let's take a look at this. The Proxy Protocol line is a single line that ends with a carriage return and line feed. That's the \r and \n. So \r for return. And it has the following form. You would have a proxy string plus a single space plus the Internet Protocol, or INET, plus a single space plus the client IP, plus then the proxy IP space, then the client port, and then the proxy port. So once we've dealt with the IP addresses, then we'll list the ports. There is not a toggle switch on the AWS management console, the toggling of which enables Proxy Protocol. In fact, the way it works is that you assign a policy to your classic load balancer. Here are some instructions. Enable Proxy Protocol using the AWS CLI. To enable Proxy Protocol, you must create a policy of type Proxy Protocol Policy Type, and then enable the policy on the instance port. Use the following procedure to create a new policy for your load balancer of type Proxy Protocol Policy Type. Set the newly created policy to the instance on port 80 and verify that the policy is enabled. Port 80 is the port associated, conventionally used with HTTP. These steps show 1. Creating a policy, and 2. Attaching the policy. So 2. Use the following create load balancer policy command to create a policy that enables Proxy Protocol. Let's take a look at the commands. So it's AWS ELB for Elastic Load Balancing, create load balancer policy, and then we've got some parameters. The first parameter is -- load balancer name. You've got to say what load balancer you're talking about. -- policy name, -- policy type name, and this is where we put that Proxy Protocol policy type. That's the type. -- policy attributes. And we can have one attribute which is Proxy Protocol and its value is true. So we say attribute name and attribute value equals 3. Use the following set load balancer policies for backend server command. What a lengthy command to enable the newly created policy on the specified port. So look, we have to create the policy and then we have this second command to get it going. Note that this command replaces the current set of enabled policies. Therefore, the -- policy names option must specify both the policy that you are adding to the list and any policies that are currently enabled. For example, my existing policy. Again, the command replaces the current set of policies. So in other words, what we're saying is if you've got 5 policies and you think, I want to add on a policy, I want to add on exactly 1 policy, I already have 5, I want to add on 1. If you use this command, which is set load balancer policies, and then you specify the one you want to add on, it will replace all 5 with the single one you have added. Oh dear. So they're warning you. They're saying what you need to do is include all 6 when you add on that one. The -- policy names option must specify both the policy you're adding And here they've given an example. It's called My Proxy Protocol Policy. So here, my in red, My Proxy Protocol Policy, and any policies that are currently enabled. You've got to write them out as well. So they've put My Existing Policy. So that's a little bit about the importance of using the -- policy names parameter. What about the application load balancer, which was announced by AWS in 2016? I can tell you now that if you bring up the documentation as a PDF and hold down the Control and F key and search for proxy protocol, you will get 0 results. Why is this? Why is it that the application load balancer, that layer 7 load balancer, does not mention proxy protocol? It's because proxy protocol intentionally does not work at layer 7. It works at the TCP level, Transmission Control Protocol, the level of the connection. A connection might underlie a number of requested packets. It's a sort of base layer that you lay down. Proxy protocol does use headers, but not HTTP headers. And so it doesn't use these headers which operate at layer 7, and that's why there's no mention of it on the application load balancer. Does the user guide for the ALB mention the traditional x_4 header, which goes back to the Harvest project and UC Boulder? Yeah, this is because this is an HTTP header, x_4. At Boulder, they did do this thing, UC Boulder, they came up with something using HTTP headers. Well, the ALB works at layer 7, so yeah, they do talk about x_4. Here's the section. Append. By default, the application load balancer stores the IP address of the client in the x_4 request header, and it will pass that header to your server, so that the server knows who's the originator here. If the x_4 request header is not included in the original request, then the load balancer creates one with the client IP address as the request value. Otherwise, the load balancer adds the client IP address to the existing header and then passes the header to your server. The x_4 request header may contain multiple IP addresses that are comma separated. The leftmost address is the client IP address where the request was first made. This is followed by any subsequent proxy identifiers in a chain. So the x_4 request header takes the following form. Take a look. x_4, and then in red, that will be the client IP address. It will be numbers separated by dots. The following is an example x_4 request header for a client with an IP address of 203.0.113.7. The following is an example x_4 request header for a client with an IP version 6 address. And these are just different ways of writing IP addresses. It's 2001:DB8::21F. Of course, this is written in hexadecimal, where we use an A for 10, a B to represent 11, a C for 12, and the columns are powers of 16. But this is not a lecture on hexadecimal. So, the ALB, just like its CLB progenitor, automatically, meaning without being configured to do so, attempts to inject an x_4 header, akin to a squid injecting ink. You know, Jeff Barr, who wrote the following when announcing the x_4 port and x_4 proto support on the CLB. Remember, they followed up from the x_4, and we got the port and protocol versions in 2010. He wrote, "These headers are injected when the request arrives at the Elastic Load Balancer. If the headers are present on incoming requests, they'll be overwritten." This is a squid injecting an x_4 header. Squids have flaps. It's an HTTP header. It works at the application layer, app. What about the NLB, which was announced in 2017? The network load balancer. Well, if I search for x_4, think of UC Boulder and squid and app, flaps on squids. It's only mentioned once. X forwarded for, and it's in a statement that explains that the ALB likes to inject this header into requests. This all makes sense. The network load balancer, which is utterly unimpressive and reliably unreachable, operates at layer 4 of the OSI reference model. It doesn't concern itself with layer 7, therefore it doesn't inject the HTTP headers known as X forwarded for. Can you enable the modern proxy protocol on your network load balancer? Absolutely. You really do just click Enable on the console, on the AWS management console. So it says Enable proxy protocol. Before you do it on a target group, meaning the thing your NLB sends things to, make sure that your applications expect and can parse that header, the proxy protocol v2 header, otherwise they might fail. 1. Open the console. 2. Under load balancing, choose target groups. 3. Choose a name. 4. On the attributes of that group, choose edit. 5. So just select proxy protocol v2. In fact, in the user guide for the Elite NLB, which is like an American Black Hawk, Chapter 6 is devoted to features of the target, the resource to which the load balancer will send traffic. In Chapter 6, it establishes that you can set up sticky sessions, which is ironic because load balancers are meant to balance traffic, and sticky sessions is continuing to send traffic to the same particular target in a target group. Chapter 6 also establishes some peculiar rules around the famous feature of NLBs, namely that they preserve the source IP address. Presumably, there are some reasons you might have to turn off client IP preservation. It would be interesting to know what these are. In other words, you might have reason for the server to only see the private IP address of the NLB and be ignorant of the client IP. Perhaps, peculiarly, if your target group uses the UDP protocol or the TCP_UDP protocol, preservation is just something you'll have to live with. If your target group uses these two protocols, then you must use client IP preservation. However, if the protocol used by the target group is either TCP or TLS, then you do have a choice regarding client IP preservation. If you so wish that your server serving only ever see the private IP of the NLB and not the client IP, then so be it. There's also something peculiar about the default settings. If your targets are not IP addresses, but rather some sort of ID associated with EC2 instances, then the preservation of the client IP is enabled until you change it. However, if your targets are in fact IP addresses, as opposed to some other ID, then you have to make an active effort to enable source IP preservation. Again, if your targets are IP addresses, which can potentially be passed amongst EC2 instances if they're elastic IPs, remember, then you have to make an active effort to enable source IP preservation. Now, why on earth is this? What is it about having IP addresses as targets for the NLB, which means that blindness should be the default? And we're concerning ourselves with TCP and TLS here. Why not have it so that IP addresses are by default able to see the true sender of the goods? I just don't understand why they've made that be the defaults in that way when they've set up the elastic load balancing product. Again, for UDP or TCP UDP, the source IP is shoved in your face and there's nothing you can do about it for UDP and TCP UDP. Preservation of the source IP is presumably a good thing. The question is whether there is any downside to it. So the question is it costly in any way to use proxy protocol? If it is, then this would explain why it is disabled by default when IP addresses are targets. I'm not aware of what this downside is, however. What I do know, however, is that we can be more certain that an EC2 instance is likely to be interested in the source IP, What I do know, however, is that we can be more certain that an EC2 instance is likely to be interested in the source IP than we can with a bare IP address. This is because applications and workloads run on EC2 instances. Well, not always, but they can do. Whereas IP addresses, the general concept of IP addresses, they're not necessarily possessed by things which are interested in source IP addresses. Look, I'm just trying to explain why it is that when the target is an IP address, we have blindness as a default. We become uninterested in the source IP. All I can say is that when the target's an EC2 instance and we use an EC2 instance ID as opposed to an IP address, then we do have preservation of the IP, because maybe the thought is that if you have an application you're interested in and it's on EC2, then you're interested in preserving the source IP. Anyhow, this is the kind of thing dealt with in Chapter 6 of that Network Load Balancer user guide. So it is features relating to the target group. It's here where we find a section entitled Configure Proxy Protocol. It's here where we find a section called Deregistration Delay. 300 seconds. Why is the value of 300 seconds important to NLB fanatics? Most people with a bit of effort can hold their breath for 300 seconds. If you haven't noticed, 300 seconds is 5 minutes. Draining, unused. These are two different states. So draining, you can think of as like the state that the cars are in when the traffic lights on the road show amber. Okay, you can go through, but we're trying to transition things to a stopped state, whereas with red, you're not allowed to drive past a red signal. That is an offence, but driving past an amber signal is not an offence. You will be given a penalty sometimes if you drive through a red signal. So this is how I think of draining and unused, the two states. Notice how it goes to unused. So it doesn't go to unavailable or unhealthy, unused. Think of a juicy tomato and a colleague left on a table for you to use in your salad, and the glowing red of the traffic light above. The unused state. A little bit of background is needed here. A network load balancer is middleman mediator extraordinaire. It's responsible for both its clients and the EC2 instances behind it. To make its life easier, the NLB only distributes traffic to targets if they are part of a container called a target group. The network load balancer always thinks of its target as being in one of 6 states. They can be summarized by an acronym. UUU-HID. UUU-HID. So there's quite a lot of words beginning with U. We've got unhealthy, unavailable, and unused. We've already looked at that. I associate unused with the glowing red, don't we? So the 6 possible states of an NLB or an ALB. Let's bring out a few points. Notice the 3 uns along the bottom row. Intuitively, there ought to be just 2 states. I mean, if you think about it, why do we have all these? Now, the 2 obvious states are joined by the double-headed arrow on the left side of the diagram. Okay? Healthy and unhealthy. Right? It's obvious that why we need those states. Healthy and unhealthy. And they're on the left side here. Then, on the right-hand side of the diagram, we find an arrow connecting the draining and unused states. The deregistration delay is the time which the NLB lingers in the draining state before dropping down to the unused state. Just as the bottom row has a common theme, the 3 uns, unhealthy, unavailable in the middle, and unused, well, so too does the top row form the word HID. So there's a common theme amongst all the elements of the top row as well. They form HID. So it's healthy, I for initial, and D for draining, HID. Think of an NLB searching out its targets. The whole matrix is remembered by hid. The top row is hid, healthy, I for initial and draining. Can you remember them? HID, healthy, initial, and draining. And then we have unhealthy, unavailable in the middle, and unused. It makes sense. That's nice that unavailable is the term in the middle. If you think about availability, it's not about a thing not existing, it's that it's just not availing itself. So it's kind of in the middle state. It's in the middle. It's not completely out of existence. It wouldn't make sense for it to be on the extreme end. It's not in existence either. So it's in the middle. So we have unhealthy, in the middle, unavailable, and then unused on the right-hand side. Remember, these are not states of the load balancer itself, but states of its target. So this is the matrix. You hid. Where are you? You hid. But hid is on the top row. Jeff Barr announced that with your classic load balancer, you could now use connection draining, and he announced that in 2014. The year that we got Lambda being announced and the Elastic Container Service. Here's what the documentation states for the classic load balancer. When you enable connection draining, you can specify a maximum time for the load balancer to keep connections alive before reporting the instance, the target, as deregistered. The maximum timeout value can be set between 1 and 3,600 seconds. But guess what the default is? How many seconds? 300 seconds. When the maximum time limit is reached, the load balancer forcibly closes connections to the deregistering instance. While in-flight requests are being served, the load balancer reports the state of a deregistering instance as in-service, instance deregistration currently in progress. When the deregistering instance is finished serving all in-flight requests or the maximum timeout limit is reached, the load balancer reports the instance state as out of service. Instance is not currently registered with the load balancer. If an instance becomes unhealthy, the load balancer reports the instance state as out of service. If there are in-flight requests made to the unhealthy instance, they'll be completed. The maximum timeout limit does not apply to connections to unhealthy limit. The maximum timeout limit does not apply to connections to unhealthy instances. And the classic load balancer has a section entitled Connection Draining. The NLB in fact calls the section in its documentation deregistration delay. But the idea is the same, so a little bit of difference in terminology. For the classic load balancer, it's connection draining, and then it's a more sort of clinical deregistration delay in the NLB user guide. Clearly, if you have expressed a preference that connections be drained, then whenever instances are deregistered, there will be a delay, because we need that time for the amber signal. The application load balancer, that also allows you to impose a deregistration delay. I suppose that what this means, bluntly, is that when you deregister a target, it is not deregistered. To put it bluntly, that's what we mean. Well, the target is not deregistered immediately, at least. This idea of draining connections is similar to the behaviour of the host on the British quiz show Mastermind. If the host is in the middle of asking a question while the time elapses, he announces, "I've started, so I'll finish." The beeper goes off saying you've run out of time, but he's still asking the question, so he says, "I'm going to finish." Similarly, if you deregister a target from your load balancer and the load balancer has a connection open with a target, the load balancer announces, "I've started, so I'll finish." All three kinds of AWS load balancers, the CLB, the ALB, and the NLB, use connection draining, which involves a deregistration delay.